Now we shall look at an example of using the AMQP or the Advanced Message Queuing Protocol with the help of RabbitMQ. RabbitMQ is a message broker. It is available as a Docker image. We can pull this image and run the RabbitMQ message broker on our system. Now I already have the image. The RabbitMQ image is present on our system. We can use this image to start the message broker. It will run on port 5672 by default. So I shall use the docker run command. Provide the host name as myRabbit. The name of the container itself would be broker and the image will be RabbitMQ. It will by default connect to the Docker 0 bridge. Right, the container has started. Let us check the Docker PS. We see this Docker container with the name broker has been started. Now we can also check that in our network diagram. So we can see this RabbitMQ server started at IP address 172.17.0.2 and it is connecting to the Docker 0 bridge. So our message broker is ready. We shall first look at a very simple program that will have a queue. It will have one producer and one consumer. As you can see in this diagram, this is a simple hello world program for RabbitMQ. We have a producer marked by P. There is a queue that is named hello, and then there is a consumer marked by C. Producer will produce the message and push on to the queues, and the consumer will then start consuming from the queues. The queue is essentially a large buffer of messages, and the RabbitMQ, the message broker, it accepts and forwards these messages. Now we have already started our RabbitMQ broker as a container. So we need to write a producer program and a consumer program. Now we can have many producers that can send message to one queue, and there can be many consumers as well. However, in this example we shall use only one producer and one consumer. So the messaging queue is based on the AMQP protocol. We can use Wireshark to capture and see the packets. So let us start the Wireshark. We shall capture packets on the Docker 0 interface. So this will capture the packets. We shall see this later when we start sending the packets. So first I shall create the producer and the consumer scripts. Now I already have these scripts written here. We shall look at the producer script first. Now the producer script, it's quite simple. First we need to establish a connection with our broker. Now the broker, as we know, it is started on the Docker container. It has this IP address. The IP address would be this. So we need to specify this as the IP address of our message broker. So let us do that. So we would have 172.17 then 2. Now this would be our message broker connection. After establishing the connection, we can declare a queue. This will create the queue if it doesn't exist, the queue name being hello. And then we will simply take an input message from the user and publish it on this queue. But before sending, we need to make sure that the queue exists. If you send a message to a non-existing queue, RabbitMQ will drop this message. Now at this point we are ready to send this message. Now in RabbitMQ, message can never be directly sent to a queue. It will be sent to an exchange. So here we are using the default exchange that is identified by an empty string. This is a special exchange because it allows us to specify exactly to which queue the message should go. The queue name is specified by the routing key, which is hello here. Now finally, when we are done, we can close this connection. Now coming to the receiving side, that is our consumer. Consumer will receive messages from the queue and print them on screen. Just like before, we need to establish a connection. So I shall use the same IP address on the consumer as well. Then we need to declare the queue. However, it is not required to declare it here if we start our producer program before the consumer. But declaring it twice will not create it twice. It doesn't make a difference here. Now receiving messages from the queue works by subscribing a callback function to this queue, which is specified by this. Whenever we receive a message, this callback function is called, and in this case it will just print whatever is received. And then next we need to tell RabbitMQ that this particular callback function should be called when there is a message from our hello queue. And finally there would be this loop that will run forever, and it will keep on consuming until we press this Ctrl+C. We give a keyboard interrupt. So with that we have our consumer and producer program ready. So let us start these programs. I will start this consumer program first. Right, the consumer program is started. It is waiting for someone to send to this queue. So let us start the producer as well. Right, the producer program is started. Now what we can do is first check the queues. We can check what queues have been created. The hello queue should have been created. So for that what we can do is start a bash shell on our Docker, or we can start it here. So start a bash shell here. Now we can see I can use this command RabbitMQ and then list queues. So we see that there is one queue with the name hello. There are no messages. So now we can start sending messages from our publisher or the producer. So this hello message was received here by the consumer. We can check our packets. We see that a lot of AMQP packets there. It was just starting the connection in there, and this is our AMQ packet that had our message in that. So like that we can keep on sending messages using a queue. So I'm going to stop this producer now, and we can exit out from the consumer as well. Now we can check our RabbitMQ here again. We can check our RabbitMQ queues. So there is the same queue. Now it is showing messages to be 0. That means there are no messages to be consumed yet. However, if we didn't start our consumer and only started our producer, let's say I send the same messages again, then these messages would be showing up here as 2 messages that are not being consumed by the consumer yet. However, once the consumer starts, it can then read these messages again. It will receive the messages and the queue will be empty again. So with this we have seen the simple queue using the AMQP protocol. We were able to send and receive messages using the RabbitMQ queues. Now we shall move on to the next part. We shall now look at the publish subscribe model for RabbitMQ. With the publish subscribe model, we can deliver a message to multiple consumers. In this example, we shall see how we can do that and publish these messages that are going to be broadcasted to all the receivers. The idea of exchange in the messaging model in RabbitMQ, the producer never sends any message directly to any queue. It only sends it to an exchange. Now the exchange in turn will send it to the appropriate queues, and it will have that information where to push which messages. Now we can specify an exchange. As shown in this diagram, this X is that exchange, and it has 2 queues here, and it can publish to both, forward this messages to both these queues from publishers. Now the types of exchanges, there are a few types of exchanges, but in this example they have used a fan out exchange, which means it is essentially broadcasting to all the queues that are bound to it. So we shall see this example and create a fan out exchange. Now the default exchange that we had used in the last example was specified by this empty string. In that case we had specified the routing key, which was the queue name. But while using exchanges, we don't need to specify routing key. Instead, we shall specify the exchange name. So this is the producer code and the consumer code from the last example or the last demo. But this time we are going to use this publisher code. It is almost the same, but the changes that we can note here is, instead of declaring a queue, we are declaring an exchange here. We are providing the name of the exchange and the type of the exchange. In producer, we had specified queue declare and given the name of the queue. The rest of the program is almost the same. We again, in the publish method, we use the name of the exchange instead of routing key. And similarly for the subscriber, we shall have the following code. Again, we shall establish this connection and declare the exchange and the type. We shall also declare this temporary queue. The name is empty, that means that name would be randomly assigned, and this queue would be bound to our exchange. And then to consume the messages from this queue, the method is the same, the basic consume method. We will have a callback function that will handle these messages. So with that, let us start our publisher and subscriber programs. I will first start the subscriber program. I will first start the publisher program. We also need to start the Docker container. So let us first start the Docker container. The container is started. Now we can start our publisher program first. The publisher is started. It is waiting for us to input a message. We shall also start the subscriber program. Yes, it is started as well. So if we send a message here, say hello, it's receiving that hello message. Now we can have multiple subscribers here. So I can start another subscriber. Now this subscriber is also assigned, it's also consuming from the same queue or the same exchange. So it shall also receive the same message. So let us say we type world here. So now both the exchanges are, both the subscribers are receiving the message. So this was a very simple example of a single publisher and multiple subscribers using exchange. Now we shall look at another example with the simulated sensor data. So we can create some sensor data and use this AMQP protocol in this publish subscribe fashion. Our sensors would publish the data, and there would be subscribers which would be, for example, programs like that store data or analyze them or control. So let us see an example of this. I'm going to stop these. Now I have a simulator here. Now I have a robotic simulator in which there is a drone. This drone has a variety of sensors built into that, including GPS sensor. So we shall take the GPS data from this sensor of this drone and send it over this exchange, send it to the exchange, and then there would be subscriber programs that would be subscribed to this data, and they will carry out different activities using that data. Now I have already added this part of code in the controller of that drone. It has a Python controller. I've already added the code to publish, to connect to the proper RabbitMQ broker, to establish the connection and then declare the exchange, and then it can publish messages. So we can use this publish message function, and it shall publish this to the required exchange. Now on the receiving side, we can have some program that will receive the data from this drone. So let us see an example of such kind of a program. First I will create a subscriber program that will just take the data from this drone and store it. I will call it sub drone. The sub drone program is first going to establish the connection, then I'm going to then declare the exchange. We are also going to bind the queue name, a random queue here, and the exchange name will be drone. We have specified the exchange name here as well. The publish host being 172.17.0.2. That is where our Docker container for RabbitMQ is running. The publish queue name or the exchange name has been described as drone, and we are using the same exchange here as well. Now we need to provide a callback function. So this would be our callback function. What it will do is simply open a new file when the drone joins or the drone is started, and it will write messages whatever it receives from the drone. That drone would be sending its GPS coordinates, that would be X, Y and Z, and that data would be written inside this drone log.txt file by this callback method. Now we can specify the consume method. So we can specify this queue name and this callback method. After that we can call the start consuming function. Now our subscriber is ready. It's going to read that data from the GPS data from the drone and write it to the log file. So we can run this one and see if it is working. subdrone.py. Right, it has started. It is waiting for the data to come from the sensors, that is our drone. So let us also start our simulation. So we shall see this simulation and our output side by side. We can exit from this one. So it has started. It has opened a new file for writing the log. Now these are the coordinates, the GPS coordinates being sent by our drone here. So we can move it around a bit and see how this program is going to record all these coordinates. So that's enough. I'll stop it now. Okay, it has stopped the controller. We can pause the simulation. However, it is still running. If we start this simulation again, or this subscriber starts receiving from this data from this drone again, it will keep on recording that. However, I'm going to stop it now. Now we can see this drone log.txt that these coordinates were recorded by our program, that was our subscriber. We can also try to visualize this. So I'm going to plot this data. We shall see. So this was the path, the trajectory followed by our drone, that was recorded by our subscriber. So now, since this was a fan out exchange, we could have multiple subscribers here. So let us create another subscriber which is also going to control this drone. So for that I can create another subscriber here. I'm going to call it CON drone for control. So the same things here, but we are going to define an additional queue that would be for sending the actions to our drone. So that queue would be action. We are not using an exchange here, we are using a simple queue, because only this program is now acting as a publisher and the drone is acting as a subscriber. So with this the drone can read from the action queue and take the action as sent by this program. So we shall create this connection as well. Now the second connection is for subscribing the data from the drone, which is through the exchange, that is our drone exchange. So we can mention that here as well. Now this connection is for reading the data, the GPS data from the drone. It will read the data, and based on the data it will take an action and send that action to the action queue which the drone is subscribed to. Now I shall create this callback function. Right, so this is the callback function. So what it is going to do is check the z coordinate of the data of the drone. So that would refer to the altitude of the drone. So what it does is simply checks if this altitude is too low, that is it is less than 0.2 meters, or if it is too high, that is greater than 2.0 meters, then it is going to issue an altitude warning, and it will also send a message to the action queue, that is to take the corrective action, that is either to increase the altitude if it is going too low, or to decrease that altitude if the drone is going too high. So it is going to publish on the actions queue, which the drone can read. So with that this program is ready. Now we need another program, that is the action has to be taken on the drone, because we didn't write any code to receive actions from this action queue. So for that I'll create another file. I will call it act drone. Now here I'm going to use this special function called control drone altitude. It is already written in the library that is available with the drone. so we can use this function to control the attitude directly. Now here we need to establish a connection to the actions queue. Then we define our callback, and now the callback would be completely handled by the control altitude, drone altitude, and we shall also print the message. So with that we can start consuming the messages from here. Right, so our act drone is ready, that is going to control the altitude. The con drone, the control drone, is simply going to give us a warning and publish this action which the drone can read. And this act drone is actually going to run, it's going to communicate with the process of the drone controller, so it can directly control its altitude from here. So we can start all these subscribers. So I'm going to reset this simulation. And then I'm going to start the sub drone first, which is going to again log the GPS positions. Let us delete the existing data. So I shall start this sub drone first. Right, the sub drone is started. Now I will also start the other one, that is control drone. Right, this process is started as well. And finally the act drone. Right, all the three scripts are now started. These are waiting for the simulation to run and the data to come from our drone. So let us see. So now I'm going to start this simulation. So let us start this simulation. Right, new log file has been created. Now this is the control drone. Now control drone is not taking action because the altitude is normal now, and that is what is outputted here. So if we try to change our altitude, let's say we move ahead a little bit and then try to go too low, as you can see it is giving a warning and then try to increase it back to normal. The same thing will happen if I try to increase my altitude too high. So say it's saying decreasing altitude, so it is automatically decreasing the altitude. I shall stop this demonstration now. We can also stop our subscribers. We can see this drone log was created. We can try to visualize this again. So this was the data that was generated by our drone flight, the path of the flight. It was recorded by our subscriber. Similarly, our control drone.py, this subscriber was also able to control the drone and stabilize its altitude. So this way we have seen that we can use this RabbitMQ and this messaging and queuing systems to collect data from our sensors and control them. This is all possible because of low latency network connections and very lightweight protocols, the AMQP protocols. So with that, let us move on to the next part. Now we shall look at some machine learning models, specifically the deep neural networks for intelligent edge. Now, object detection is an important application of computer vision. There are many models for object detection such as RCNN and YOLO. We shall look at one such model that is called YOLOS with an S. YOLOS was proposed in this paper. It stands for you only look at one sequence. So it's an implementation of object detection through vision transformers. VIT has been already proposed by authors. So they have used the vision transformers in place of convolution neural networks. Now this transformer model, it divides that input image into patches, which is treated as a sequence and then fed into the encoder, which then uses this transformer architecture, and it uses it to predict the bounding boxes, the B boxes here, and the classes. So we shall look at this model. There are various different models such as YOLOS for image processors, feature extractors, but we shall look at the one for object detection. Now this model is available on the Hugging Face website for transformers. We can get a pre-trained model here. This is based on PyTorch. So there is an example given here on how to use this YOLOS model. So they have used the YOLOS tiny model. We shall also use this tiny model and use it for inferencing. So let us see with this example how we can do that. So I will create a new notebook file here, and then we can use this code, existing code. So make the imports first. Now we need to define the image processor and the model. We shall use this YOLOS tiny model. Right, the model will get downloaded from the internet. However, I have this model already, so it's going to use it from the cache. And then we also need to define our image, that is the input image. So the input image is going to be taken from this URL. We can see what this image looks like. So this is an image of two cats lying on a couch. There are two remotes as well. So now we can input this image into our model. And it will produce the outputs. Now we need to process the outputs as well. So we shall use this piece of code. Right. So it's also going to tell us the bounding boxes, the location and the size of the bounding box. So we shall see the output of this model. So it has detected a total of 5 objects, out of which 3 are remote, although there are 2 remotes here, and there are 2 cats. And these are the bounding boxes. Now we can also draw these bounding boxes. This will plot the bounding boxes and also annotate the object with the class label. So let us see this bounding box. I forgot to import this one. I'm still getting some error. Right, we have not defined item here. Let me redefine this one. Yes. Yes, so now the bounding boxes are showing up. So it has detected 2 remotes on the same one. There's a remote detected here and the cat detected here, the other cat detected here. So we can look at a few more examples. There are a few more example images. So I have some images here. This is an image of a person sitting at an office. So let us see what our model detects. So our model has detected 4 objects here, 2 of which are potted plants, 3 are potted plants, and 1 is a person, as we can see in this image. We can look at one more example here. Let us try some other image. This is the image of 2 cows. Let's see what our model outputs here. It has detected 2 cows correctly. We shall look at one last example. Right, our model has detected a bus, so many cars, there's a clock detected here and a person detected here. So this model works quite well, fairly well. So we can use this model to detect objects. We shall look at an example where we shall use this with our drone earlier from the simulation. The drone also has a camera, so the camera can be used, the data from the camera images. So I have this setup. We have a few objects. There's a box, there's a cat, there's a person, a car and a chair. Now the controller here has already been programmed to send images. but we need something to handle these images and pass them through our YOLO's model for object detection. Now YOLO's model can only detect objects in an image, so we have to extract frames from the video and then pass it to the YOLO's model for detection. So let us create new file here. Now here I'm going to use the same model that I'd used here. So the imports here, the model YOLO's tiny, and we shall also listen to one of the or subscribe to one of the exchanges, the same drone exchange that would be running at this IP address. Not the drone exchange, but the RabbitMQ broker would be running at this IP address, and there would be an exchange called drone. And previously the drone was publishing its GPS data on the exchange, but this time it's publishing its images, the camera images, and we have to read those camera images from our script or our program and pass them through the YOLO model to detect the images, the objects. So for that we already have defined this exchange. We need to define a callback that is going to process our data. So let us define this callback. So this is our callback. I've used the same code from the previous one for detecting the object and drawing bounding boxes around them. And this is what happens in the callback. The detection will happen in the callback and it will output the image with the bounding boxes. And this is going to happen as long as there are messages to be consumed, that is, the images are being sent by the drone. So our consumer here is ready with the YOLO model inside it, and it can start consuming. We can run this one. Right, our consumer has started. It is waiting for the drone to transmit its data. So let us also start our simulation. Right, now we need to switch on the drone camera. The camera is on. And we see here that we have started receiving these images from the drone. Now it is not able to detect this box properly. However, we shall move this drone around and see if it is able to detect the other objects or not. So I'll slow down the animation, the simulation, and turn this drone around slowly. Right, our drone has started turning around. Let us see if it is detecting the other objects or not. So I shall scroll to the bottom here. Right, here we see that this cat has come into the frame. However, it has been detected as a cow. This dummy is being correctly detected as a person. And then the car has come into the frame. It is also being detected correctly as car. So as our drone turns around, it is detecting all the objects. This chair has been detected as a bench. It's not correct, however it is close. So now it has moved to the other view. We can turn this drone around again. We can wait for it to turn around again and go for a second route of detection. We can try to increase its height a little bit to get a different view. We shall turn back a little bit. And look at it from a higher perspective. Let's see if there's any changes in the detection. The cat is out of frame. It is not being detected correctly. However, this person is being detected correctly. Now the cat again being detected as the cow. The car is being detected correctly. However, its wheel has been detected as a clock. Now we did not train this or fine-tune this YOLO's model on our data, that is the images from our camera. Now although this is a simulation, these objects might not accurately represent the training data. However, our model is still performing fairly well. It is able to detect some objects such as the car and the person. It has detected correctly. Now I'm going to stop this simulation. Right, the simulation has stopped. Now we can stop our subscriber as well. So in this way we have seen the working of YOLO's model. We installed this YOLO's model on our drone. Not exactly drone, the YOLO's model was in fact running on the edge, that is our host, and it was communicating through that Docker 0 bridge with our broker, that is RabbitMQ, and this drone was sending all its data, the camera feed, through the RabbitMQ queues, and that was being received here by our subscriber that was running on the edge, not on the drone itself. And it was running this YOLO and it detected whatever it could, and with that we have seen this YOLO model. Now we shall look at some more such models in the next part. So with that let us end this one here. I'm going to exit out of this simulation.